Welcome to this lecture. This lecture is based on spin angular momentum, and here in this part I will talk about the idea of spin angular momentum. So let us discuss that how people got idea of spin angular momentum. The idea of spin is revealed in 1922 while Otto Stern and Lecture-Gerlach these two scientists performed an experiment what they did in their experiment, they have taken a magnetic field applied along z-axis, right, and they pass through it beam of silver atoms. They pass through the magnet. What they got on the screen, they observed two spots like this, right? That means if this is the screen, then on the screen they saw such type of observation. One spot they saw here and another spot they saw here, right? So what causes these two different spots in their experiment? That's the important thing. So let me write down some briefing about this experiment. That what they did, they passed a beam of silver atoms through the poles of a magnet, or in other words we can say that across the magnetic field, and in this experiment they applied magnetic field along z-axis, and they observed two bands, right? They observed these two bands, one here and another band is here. Now let us try to that what we are expecting through this experiment. Expectation from this experiment. Let me recall electronic configuration of silver atom. Electronic configuration of silver atom. Silver atom, its atomic number is 47 and its electronic configuration is krypton 4d10 5s1. It is one unpaired electron, rest of the electrons are paired. So let us try to look at. There are two possibilities whether this 47th electron in 5s orbital, or there is a possibility this 14th electron may be in 5p orbital or the 5p state, right? So if it is in 5s state, for this the value of J will be, angular momentum will be equal to 0, and corresponding to it, its Z component is also 0, or we can say that for L is equal to 0, ML is equal to 0, right? And if it is in 5p state, then J is equal to 1, and Jz possible values of -1, 0 and 1. There are 3 possible states, or in other words I can write down it as L is equal to 1 and ML is equal to -1, 0 and 1, right? Both are representing one and same thing. That means corresponding to now what we expect, so we expect either one spot corresponding to 5s state, or we are expecting 3 spots corresponding to 5 state. That means, this means 2 states are not expected. So what causes different, or what causes these 2 spots and how people solve this puzzle? So this puzzle was solved in 1925, means after 3 years. Why? Samuel A. Goudsmith, and George E. Allenbeck. These are the 2 scientists who tried to solve this puzzle. What they did, they suggested that electrons contain intrinsic angular momentum and this intrinsic angular momentum gave a magnetic moment and interact with applied magnetic field, and let S be the spin angular momentum as there are two spots as observed experimentally. That means its Z component must have two values. That is, its Z component must have two values. That is, 2s plus 1 always must be equal to 2. Means these are the possible values of Sz. Right. So from here, S comes out to be 2 minus 1. So S is equal to 1 by 2. So this is the spin angular momentum. This is the value. And the values of Sz is equal to minus 1 by 2 to plus 1 by 2. So right, so this is a way that how I can write down the possible values of, right. So that's why we call that spin is always half for the electron. And spin is purely a quantum mechanical effect. Quantum mechanical effect. Right. This is a very interesting thing. Now the possible eigenstates for electron. Now the possible eigenstates for electron in terms of spin can be written as SMS, and that is 1 by 2, 1 by 2, comma 1 by 2 minus 1 by 2. So these are the two cuts which are representing eigenstates for the electron in terms of spin. As we did in case of orbital angular momentum or general formalism of angular momentum, on the same basis other formalism will remain the same. So let us have a brief look at that. Eigenvalue of S square operator can be written as S square Sm. It is equal to S into S plus 1 H cross square SMS, and it is equal to 1 by 2 plus 1 H cross square S into MS, or it is 3 by 4 H cross square SMS. And from here I can write down the value of S is equal to root 3 by 2 H cross. Also, Z component can be written as Sz SMS. It can be written as MH cross or MSH cross S ms. So that means ms has two possible values, plus minus 1 by 2. So it means plus minus 1 by 2 h cross sms. And let us try to write down or express this graphically. So graphically this can be represented as here s is equal to root 3 by 2h cross. It is also root 3 by 2h cross, and corresponding to it, its value will be plus h cross by 2, and here it is minus h cross by 2. So this is the graphical representation, and this angle comes out to be 54.73 degree, and this angle comes out to be minus 54.73 degrees. So these are the quantized angles which we are getting. And some important formula or some important formulation. This is similar to as we did in case of orbital angular momentum. So like Sx, Sy, its commutator is equal to iota s cross h cross sz. Sy, Sz, its commutator is equal to iota h cross Sx. Sz, Sx, and its commutator is equal to iota h cross Sy. And S square Sms is equal to h cross square s into s plus 1 sms, and sz is equal to szms is equal to h cross ms sms. Then s plus minus is equal s plus minus sms, it can be written as h cross s into s plus 1 minus ms into ms plus minus 1 whole under the root sms plus minus 1. Then sx square is equal to sy square and is equal to 1 by 2 s square minus sz square, and it comes out to be h cross square by 2 s into s plus 1 minus ms square. Also, normalization and completeness conditions can be written as s prime ms prime sms is equal to delta s prime s and delta ms prime ms, and the completeness condition ms is equal to minus s2 plus s sms sms is equal to 1, right? So that's all for the idea of spin angular momentum, and in the next lecture I will talk about spin half and the Pauli matrices. So thanks for watching this lecture.